Hello, everyone. Welcome to today's presentation. I'm Kainat Raisa-Hussain, and today I'm going to be presenting a research paper called Mind's Eye of LLMs, Visualization of Thought Elicits, Spatial Reasoning in Large Language Models. To give you a quick overview of today's presentation, there will be basically four main sections of our presentation today. There will be an introduction section of the paper and all of the introductory part of the research paper. Then there will be a second section which will have the related works. Then the third section will have the experiment and results this research paper has dealt with, and the last part will be the conclusion. So the introduction part. What this research paper is basically trying to solve. I mean, what is the problem statement this research paper actually deals with? So basically, this research paper explores LLM's abilities to manipulate mental images for spatial reasoning, similar to the human cognitive process known as the mind's eye. So what is basically we mean by mind's eye? The mind's eye refers to the human ability to create and manipulate mental images of unseen objects and actions, as well as unseen events. Let's take an example. Suppose we want to go to a particular place. So before heading towards it, we visualize inside our mind that how we are going to reach to that place, which route we are going to take, and what are the objects and what are the things that we'll pass by in our journey. So this visualization power of human being is basically called mind's eye. Another example can be a human solving puzzles. When we solve a puzzle, before starting to solve that puzzle, we try to visualize how the whole picture of the puzzle will look like once it is solved. So which piece will be positioned in which place, our ability or humans' ability to imagine these things, to reason these things inside our mind is basically called as mind's eye. Then what's spatial reasoning? Spatial reasoning is basically a part of mind's eye. Mind's eye is basically a part of human cognition. So spatial reasoning is actually the capability of human being to understand and reason about the spatial relationships between objects and their movements. So what this research paper actually proposes. The paper proposes that LLMs can be prompted to generate and utilize visualizations of their internal reasoning states, thereby improving their performance in spatial reasoning tasks, such as navigation and visual tiling. Basically, the researchers of this paper say that they basically state that LLMs can be prompted to achieve this special reasoning ability like human being. So what is the approach this research paper or the researchers of this research paper are basically introducing to us? This research paper introduces to us a prompting technique, which is called visualization of thought. What is visualization of thought prompting? This is simply just instructing the LLMs to visualize the state after each reasoning steps through our prompt. So for this research paper, the researchers have developed VOT prompting technique and evaluated its effectiveness utilizing GPT-4 and GPT-4 vision models with various prompts on 3 specific tasks requiring special awareness: natural language navigation, visual navigation, and visual tiling. These are the 3 tasks that this research paper has taken to do the experiment for evaluating the effectiveness of VOT prompting. The first one is the visual navigation task. The second one here is the visual tiling task. And the third one is the natural language navigation task. 3 of the tasks require our LLMs to have special reasoning power to solve them efficiently. This is an image which basically shows what we refer to mind's eye of human beings and what we refer to mind's eye of LLMs. Here the upper half of the image shows that the example I have given at the beginning, what we actually understand by mind's eye of human being. So in LLMs, it can be LLMs can also achieve the same power, the same special reasoning power through a specific prompting technique. So here we can see the other half of the image shows us that the comparison of different prompting techniques and how LLMs perform based on that prompting technique. For our conventional prompting technique, what we do, we basically just ask the LLM to directly generate the output. For example, I want to write a neural network, an article on neural network. So I will ask the LLM to like this. I will write the prompt like this, that write me an article on neural network. So it will generate an output. Then in the chain of thought prompting method, we'll additionally we'll ask the LLM to generate to write us an article on a neural network, but we'll additionally ask the LLM to think step by step for doing the task. Then comes the visualization of thought prompting, which this research paper actually proposes. We will not only ask our LLM to visualize, to break down, to think step by step, but also we'll ask the LLM to visualize each step after completing the step. So this is what the idea of visualization of thought prompting is. Then there comes a section which has the related research works that have been already done previously. So the related research works that has been done before, we can categorize them in broader categories. So some of the broader categories, among the broader categories, there is a category which is basically special reasoning over text, where the research papers, the previous research papers, have dealt with semantic representation and special information extraction. The papers basically focus on representing spatial relationships and extracting special information from text. Then there is another thing that multiple research papers have dealt with, the learning and reasoning in NLP, where the papers have explored a learning and reasoning mechanism in natural language processing tasks involving special reasoning. Then there is another category of work that has been done. Advancements in large language models. The research papers have worked on improving multi-hop spatial reasoning, where they involved pre-training LLMs with synthetic data sets to enhance their ability to perform multi-hop spatial reasoning tasks. Then there are some works that have worked to develop data sets, to the development of data sets. The development of data sets covering various spatial relations in 2D visual scenes, geometric patterns, and 3D spatial information. Then there are a couple of researches that has been done on UI grounding and in-context learning, where they have investigated using LLMs for UI grounding and converting spatial information into logical forms. Then the last broader section, broader category, we have here for our previous related research papers, world models of LLMs, where the researchers have dealt with the internal world modeling, where they have explored whether LLMs can effectively learn internal world models solely from ungrounded forms. And besides that, they have also worked on internal representations, where some studies showing LLM's internal representations can be mapped to grounded perceptual and conceptual structures in domains like color and spatial reasoning. So this is the third section of our presentation, which will have the experiment this research paper has done, and the researchers of this research paper has done, and the results they have come up with. So basically, the experiment is like this research paper mainly utilizes GPT-4 and GPT-4 vision models as LLMs with various type of prompts to evaluate the effectiveness or how VOT prompting actually work by comparing the VOT prompting technique with other prompts. Here we can see they have used 4 prompt variants. Firstly, they have used GPT-4 model with COT prompting technique, where they have included the phrase in their prompt, which is "let's think step by step." Then, secondly, they have used GPT-4 model, where they have explicitly disabled the visualization of the LLM. So they have used the phrase "don't use visualization, let's think step by step" in their prompt. Thirdly, they have used GPT-4 vision model with COT prompting technique, and they have just used the phrase "let's think step by step" in their prompt. And finally, they have used GPT-4 model with the GPT-4 model has been used along with VOT prompting technique, where the researchers have used visualize the state after each reasoning step in their prompt. And now the description of the data set that has been used in this research paper. For the natural language navigation task, used 3x3 sized 200 square maps were used for this task, where each map had 3 landmarks arranged in snake order traversal. And there were a set of instructions were provided for navigating the maps. And for the visual navigation task, there were 496 navigation maps were generated, and a total of 2,520 question answer instances were used. And The purpose of this experiment is basically the dataset assesses the ability of models to navigate visual environments based on provided maps and instructions. Then the third task, visual tiling, where multiple unique configurations were used to fill a 5x4 rectangle. Polyomino pieces, 5 polyomino pieces were used, where two were 2I tetraminos, 2T tetraminos, and 1L tetramino. Then each configuration was masked randomly with 2 or 3 pieces generating 796 QN instances. So what is the objective of this particular task? This task evaluates how well models can reason about special arrangements and solve tiling problems. And here are the results that this experiment gives us. The results shows that GPT-4 model has with VOT prompting has outperformed all of the other prompting or prompts or prompting techniques by achieving 40.77 completion rate for visual navigation task and 14.72 success rate for the visual navigation task. And for this task, it has achieved next step 55.28 accuracy for next step prediction. And we can see that for for visual tiling and natural navigation task as well, the GPT-4 model has outperformed all of the other prompts that were used in this research paper. Then we have seen so far that the researchers have mainly used the two of the advanced LLMs, which are the GPT-4 and GPT-4 Vision. But what about the less powerful LLMs? So here, later on the research paper, the researchers have employed 3 other less powerful models with VOT prompting, and they have tried to evaluate how VOT prompting works with the less powerful LLMs. So here we can see that the GPT 3.5 model, for the GPT 3.5 model, the VOT prompting technique has outperformed the visual navigation task in terms of completion rate. But for the visual tiling and natural navigation task, the GPT 3.5 model has outperformed the COT prompting technique. Then for Llama 3 8B model, we can see that there is in some of the according to some of the matrices, based on some of the matrices, the VOT prompting has performed better for visual navigation task, but for the visual tiling and natural navigation task, it hasn't been able to perform that well. Then for the Llama 3 70 billion model, the VOT prompting technique has outperformed in terms of all of the matrices for the visual navigation task. But for the other 2 tasks, especially for the visual tiling task, it hasn't performed that well. But for natural navigation task, it has performed well. So what we can say from here, that for less powerful LLMs, the the VOT prompting technique doesn't give us a consistently good result for each of the LLMs, as well as based on each matrices. Then here comes the concluding part of this research paper, where the conclusion basically says that the research paper basically concludes that VOT prompting effectively enables LLMs to develop and utilize a mind's eye for spatial reasoning. The study demonstrates us that the potential of VOT to enhance cognitive and reasoning abilities in LLMs. Future applications in multimodal large language models could benefit significantly from integrating VOT. Further exploration into diverse and complex representations of mental images is recommended to bolster LLM's spatial reasoning capabilities. This paper underscores the importance of continuing advancement in spatial reasoning to broaden the applicability of LLMs in complex real-world scenarios. And here comes the limitations or the challenges this research paper basically has, that this the VOT prompting, the result, the effectiveness of VOT prompting basically depends on how advanced the LLM is. So the VOT prompting effectiveness hinges on advanced LLM capabilities, potentially limiting performance gains in less advanced models. Then there is another challenge, which is the sensitivity to prompts. Visual state tracking in LLMs is sensitive to prompt specificity. Explicit instructions like use ASCII art enhance performance, while vague prompts may reduce tracking rates, which basically means that the VOT prompting technique, the effectiveness of the VOT prompting technique, which also depends on the sensitivity of also depends on the prompts, how we are writing the prompt and what prompt is given to the LLM. Then there is another limitation, which is this VOT prompting technique, or this is basically limited. This research paper has utilized limited data and instruction tuning, where the current approach lacks extensive data exposure and explicit instruction tuning, which affects the robustness and generalizability of visual state tracking in LLMs. Then the last limitation we can talk about is the scope of mental images. The study's mental imagery is confined to 2D grids, underscoring the need for research into broader representations like complex geometric shapes and 3D semantics to enhance spatial reasoning capabilities. This is the paper link. And